In the dark waters off the coast of Britain during World War II, death lurked beneath every wave. German mines, thousands of them, lay silent and patient on the seabed, waiting to tear apart Allied vessels with devastating force. These weapons of terror didn't discriminate between battleships and supply convoys, between military targets and civilian cargo. They were indiscriminate killers, and they were winning. But the real horror wasn't just the mines themselves. It was the impossibility of fighting an enemy you couldn't see. Imagine, for a moment, descending into those frigid waters. The pressure builds around you with every foot you sink. Your heavy diving suit restricts every movement. Your air hose is your only lifeline to the surface. And ahead of you, somewhere in the murky darkness, is a German mine containing enough explosive force to vaporize you instantly. You need to see it. You need to find it before it finds you. But here's the cruel irony that defined early mine clearance operations. The very tool designed to help you see was actually your worst enemy. Traditional diving lights of the era were primitive by any standard. They produced a diffused, scattered glow that illuminated everything and nothing at the same time. In clear water, they might offer some visibility. But in the turbid, sediment-filled coastal waters where German mines were concentrated, these lights created more problems than they solved. The diffused beams scattered off suspended particles, creating a blinding fog of light that made navigation nearly impossible. Divers described it as trying to drive through a blizzard with your high beams on. Everything became an indistinct haze of gray and white, and the mine you were searching for remained invisible until you were close enough to touch it. But the problems with conventional diving lights went far beyond mere visibility. In the tactical environment of World War II, light meant death in another way entirely. German observers, whether on shore installations or patrol vessels, could spot a diver's diffused light signature from remarkable distances. That soft glow emanating from beneath the waves was like a beacon announcing to the enemy, "Here I am, and here's exactly where you should drop your depth charges." Allied divers weren't just fighting blindness. They were advertising their positions to an enemy that was more than willing to eliminate them before they could reach their targets. Every mission became a gamble, where the odds were stacked impossibly against survival. Every dive could be your last, and the statistics proved it. Casualty rates among mine clearance divers in the early years of the war were catastrophic. The man who would revolutionize underwater mine clearance was as unconventional as the solution he proposed. Dr. Alistair Finch was a Cambridge-educated optical engineer who had spent the pre-war years working on specialized lighting systems for industrial applications. He was brilliant, stubborn, and possessed of the kind of lateral thinking that drives military bureaucracies absolutely mad. While career naval officers saw underwater illumination as a simple problem with simple parameters, Finch saw it as a complex optical challenge that required reimagining the fundamental principles of how light behaves in aquatic environments. He didn't want to make diving lights brighter. He wanted to make them smarter. Finch's proposed design was radical for its time. Rather than creating a light that illuminated a wide area, he envisioned what he called a directed illumination guide, a system that produced an intensely focused, narrow beam of light that could cut through turbid water like a laser cuts through smoke. The design incorporated a series of precisely arranged lenses and reflectors housed in a pressurized cylinder with an adjustable aperture that allowed the diver to control beam width based on water conditions. But the truly revolutionary aspect was the guide mechanism itself, a framework of light-permeable tubes and directional indicators that helped divers maintain proper distance and angle from potential mine casings while keeping the focused beam on target. It was ingenious, it was unprecedented, and Naval Command hated it. The official rejection came swiftly, and with considerable force. The assessment from the Admiralty's Technical Evaluation Board was damning. They declared Finch's design too complex for field conditions, too fragile for the rigors of combat diving, and too resource-intensive to manufacture during wartime rationing. But the real reason for rejection was more fundamental and more human. It was simply too different. Military institutions, particularly in the midst of war, tend toward conservatism. They prefer incremental improvements to existing technology over revolutionary new approaches. Finch's lantern guide represented a complete paradigm shift in underwater illumination methodology, and that made admirals nervous. There was also the liability question. If this experimental device failed and divers died as a result, who would be held accountable? Better to stick with conventional equipment, even if that equipment was inadequate, than to risk careers on unproven innovation. The official designation of Finch's project was changed from under evaluation to not recommended for implementation. In practical terms, his lantern guide was banned before it ever got wet. But war has a way of exposing the difference between bureaucratic caution and operational reality. Through the autumn and winter of 1942, mine clearance casualty rates continued to climb. Convoys were being lost. Critical harbors remained unusable because mines couldn't be cleared efficiently. The human cost was mounting with every failed mission, and field commanders were becoming desperate for any solution that might turn the tide. It was in this environment of mounting pressure that Captain James Holloway, a senior mine clearance operations officer, made a decision that could have ended his career. Holloway had heard rumors about Finch's rejected design through informal channels, the kind of talk that happens in officers' clubs after the third whiskey. He'd read the technical specifications that had been filed away and forgotten. And unlike the evaluation board that had dismissed the concept from the Safety of London offices, Holloway had actually been underwater. He'd experienced firsthand the lethal inadequacy of standard diving lights. He understood what Finch was trying to solve because he'd watched good men die trying to work around it. So Holloway did what desperate commanders sometimes do. He found a way to make it happen without official approval. Using discretionary operational funds and calling in favors from supply officers who knew better than to ask too many questions, he contacted Finch and authorized the construction of 3 prototype lantern guides. The units would be built, tested, and deployed without official sanction. If they failed, Holloway would face court-martial. If they succeeded, maybe someone would look the other way. The prototypes that Finch delivered weren't exactly what he'd originally proposed. Working with Holloway and experienced mine clearance divers, he'd made modifications based on practical field requirements. The housing was reinforced with available materials, designed to withstand impacts against mine casings and underwater obstacles. The lens assembly was simplified to reduce the number of precision components required, making field repairs possible. And critically, the guide framework was redesigned to be more intuitive, with luminescent markers that divers could see even in complete darkness. These weren't the perfect embodiment of Finch's vision, but they were what could be built quickly, covertly, and effectively with the resources at hand. They were combat-ready improvisations born from the marriage of theoretical brilliance and practical necessity. The first operational test happened on a moonless night in March 1943, off the coast of Cornwall. 2 divers descended into known mined waters carrying Finch's illegal lantern guides, while a 3rd diver with conventional equipment served as control. The mission parameters were simple: locate and mark 3 confirmed German contact mines for subsequent disposal. The diver with standard equipment spent 42 minutes in the water, located 1 mine, and surfaced with signs of severe stress and disorientation. The 2 divers with Finch's guide spent 31 minutes underwater, located all 3 mines, and surfaced reporting clear visibility and precise navigation throughout the operation. One of them later wrote in an unofficial log, "It was like someone turned on the lights in hell. For the first time, I could actually see what I was doing down there." Word spread quickly through the mine clearance diving community. Within weeks, divers were specifically requesting assignment to units that had access to the special equipment. The technical brilliance of Finch's design became evident in actual combat operations. Unlike conventional lights that scattered illumination in all directions, the focused beam from the lantern guide could penetrate turbid water with remarkable efficiency. The narrow beam concentrated light energy along a specific path, reducing scatter and backscatter that had plagued standard equipment. At optimal settings, a diver could achieve clear target visibility at distances of 12 to 15 feet, compared to the 3 to 4 feet maximum with conventional lights. This increased standoff distance was literally life-saving, giving divers time to identify mine types, assess triggering mechanisms, and plan approach vectors before getting within danger-close proximity. The guide framework component proved equally revolutionary. Finch had incorporated a series of parallel tubes that ran alongside the light housing, constructed from translucent materials that allowed ambient light from the focused beam to illuminate graduations and markers along their length. These served as visual reference guides, helping divers maintain proper distance and angle of approach to suspected mines. A diver could align the guide markers with a mine casing and know immediately whether they were at safe working distance or had drifted dangerously close. This spatial awareness, impossible with traditional equipment, transformed mine clearance from a game of blind touch and hope into a controlled, methodical procedure. For men working in an environment where a single mistake meant instant death, this represented nothing less than a revolution in operational safety. The focused beam also solved the enemy detection problem that had plagued earlier operations. The narrow directed light was far less visible from surface observation points because it didn't create the diffused glow that traditional lights produced. German coastal observers looking for diver activity would see nothing, while the Allied diver below maintained clear visibility of their target. Multiple after-action reports noted that operations conducted with Finch's guides experienced no enemy interference, while operations in adjacent areas using conventional equipment continued to draw hostile response. The lantern guide had effectively rendered mine clearance divers invisible to enemy observation, while simultaneously giving them unprecedented underwater visibility. One diver, whose account was preserved in classified post-war interviews, described his experience with extraordinary clarity. Lieutenant Robert Thorne had been conducting mine clearance operations for 8 months before gaining access to Finch's guide. He'd lost 3 members of his dive team to mine detonations and enemy action during that period. His first mission with the new equipment was clearing a cluster of German Type C mines from the approaches to Portsmouth Harbor. In his words, "I descended expecting the usual murk and anxiety. What I got instead was precision. The beam cut through that dirty water like nothing I'd experienced. I could see the mine casing, could identify the horn detonators, could plan my approach vector, all from a distance that felt safe. For the first time in my diving career, I wasn't just reacting to shadows and shapes. I was working with clear visual intelligence. We cleared 7 mines that night, more than my team had managed in the previous 2 months combined." The operational impact was measurable and significant. Units equipped with Finch's guides reported mine clearance rates that were 2 to 3 times higher than units using conventional equipment. Casualty rates in equipped units dropped by approximately 60% within the first 6 months of deployment. Critical harbors that had been deemed too dangerous for clearing operations became accessible. Convoy routes that had been closed due to mining were reopened, allowing vital supply lines to resume operation. One senior logistics officer later estimated that the accelerated mine clearance enabled by Finch's technology saved at least 15 major cargo vessels and 3 escort destroyers in the latter half of 1943 alone. Those ships, in turn, delivered thousands of tons of supplies and equipment that supported combat operations across multiple theaters. The official recognition for this life-saving innovation was, perhaps predictably, virtually non-existent. Because Finch's Lantern Guide had been developed and deployed outside official channels, it existed in a bureaucratic gray zone throughout the war. Technical reports mentioned improved illumination equipment without specific attribution. After-action reports credited enhanced operational techniques without detailing the technology that enabled those techniques. Dr. Alistair Finch received no medal, no commendation, no formal acknowledgement of his contribution to the Allied war effort. Captain Holloway, who had risked his career to give the design a chance, received a minor administrative reprimand in 1944 for irregular procurement procedures before being quietly promoted and transferred to another command where his initiative would be appreciated. The few divers who knew the truth kept it among themselves, bound by the informal codes of secrecy that governed clandestine wartime operations. In the immediate post-war period, when so much attention focused on dramatic aerial combat and large-scale ground campaigns, the unglamorous work of mine clearance diving received little public attention. The men who had defused hundreds of German mines using illegal equipment went back to civilian life without fanfare, carrying their stories privately. Some wrote memoirs decades later that hinted at the specialized equipment they'd used, but by then, the names had been forgotten and the technical details had faded into historical obscurity. Finch himself returned to academic life after the war, resuming his work on industrial lighting systems. He published several papers on focused beam technology and optical engineering, some of which contained veiled references to wartime applications. Colleagues who knew his history understood the subtext, but the broader scientific community never made the connection. When Finch died in 1967, his obituary in the Times made no mention of his contribution to mine clearance operations. The Lantern Guide that had saved countless lives remained classified in Admiralty archives, accessible only to historians with appropriate clearances and specific reasons to go looking. But technology has a way of honoring its pioneers even when official institutions fail to do so. The principles that Finch incorporated into his underwater lantern guide, focused beam illumination, adaptive aperture control, integrated spatial referencing, have become foundational elements of modern underwater optical systems. Contemporary mine clearance operations employ remotely operated vehicles equipped with high-intensity focused lighting that directly descends from Finch's innovations. Commercial diving operations use spatial referencing systems that bear remarkable similarity to his guide framework design. The military and commercial diving communities that benefit from these technologies rarely know the name Alistair Finch, but they're using tools that embody his vision every single day. There's a broader lesson here that extends beyond the technical specifications of diving lights and mine clearance procedures. World War II was won not just by generals and grand strategies, but by countless small innovations conceived by unconventional thinkers and enabled by commanders willing to bend rules for operational necessity. The war rewarded adaptability, creativity, and the courage to challenge established doctrine when that doctrine was demonstrably failing. Finch's illegal lantern guide represents a class of innovation that exists in the shadows of official history. Solutions born from desperate necessity, implemented through informal networks, successful despite institutional resistance, and forgotten because they were never supposed to exist in the first place. How many other stories like this remain buried in classified archives or lost to institutional memory? How many other brilliant engineers, maverick officers, and brave operators contributed critical innovations that never received recognition because they worked outside approved channels. The historical record, particularly of military operations, tends to document successes that fit approved narratives while quietly forgetting the messy, irregular innovations that actually made victory possible. We celebrate the Spitfire and the Sherman tank because they came from official development programs with proper documentation. We forget the illegal lantern guide because it was built in a workshop using discretionary funds and deployed by commanders who knew better than to ask for permission. As we reflect on these forgotten innovations and unsung heroes, we're reminded that progress often comes from unexpected places, from people willing to challenge conventional wisdom even when institutions resist. The divers who descended into dark waters carrying Finch's banned equipment didn't do so because admirals ordered it. They did it because someone recognized a problem, designed a solution, and found a way to make it happen despite official disapproval. That spirit of innovation under adversity, of problem solving through determination rather than authorization, represents one of history's most valuable lessons. The next time you hear about some new technology or methodology that seems too radical, too different, too far outside established practice, remember the story of an illegal lantern guide that diffused hundreds of German mines and saved countless lives. Remember that sometimes the most important innovations are the ones that never should have existed at all, brought to life by people who refused to accept that impossible meant impossible. History may not remember their names, but their legacy illuminates our world in ways we're only beginning to understand.